Hi, welcome to Module 5 of Lecture 12. This is the first of 3 modules talking about, well, providing a very rough introduction to the topic of stochastic processes, and particularly Markov processes. Now, a stochastic process, and then there are a whole class on this stuff, so it's going to be very rough and very quick, just to give you a sense in how you can use matrices and also vectors and matrices and stuff similar to eigenvectors and eigenvalues as well. To understand real-world processes. So a stochastic process is really a process in which there's some random component to how the state of the system evolves. Really formally just a collection, a set of random variables. But we'll talk about it a little more concretely. So let's say you have some state of the system. Now, state here is an important term, state. And a state can be almost anything. It is an incredibly broad term. It could be the present state of conflict between every country in the world, where you put 1 or 0 for conflict. It could be the present net influx or outflux, I guess, of trade between every country in the world. It could be approval ratings for all candidates in some coming election. Or it could be president approval ratings for every politician in the country. Right? It can be anything you want it to be, pretty much. Right? A state just tells you what the world is like at that moment. The point of stochastic processes, in a nutshell, is to help you understand how states evolve over time. We discussed this a little bit in the previous modules in this lecture. We called something S sub t and said that was a state vector at time t, and talked about how it transitioned between a state vector at time t and ended up at some state vector at time t plus 1. We'll talk a little more about this in a second, but the idea is just that the stochastic process tells you how the states of the system, it tells you what the state is and how the states of the system evolve over time according to some rules. And typically, as befits the word stochastic, the evolution of the system is in itself has some random component to it. It's not guaranteed you end up deterministically at a certain spot, as it was in, say, a difference equation that we talked about. Rather, the system could go somewhere with some probability. Now again, states can be very general, so the stochastic process could tell you the chance of going to different states of war between countries or trade or anything. States can be continuous, they can be discrete. You could have a state which consists of sort of GDP for all countries in the world, and that could be continuous effectively. So you could have an infinite number of possible values for these things. Or it could be a discrete thing, in which you have a set number of countries, and each country could be at war or not at war with someone. So that's a state vector that would be represented by a state vector consisting only of the number of countries in the world, with a 0 for no war and a 1 for war somewhere. It's a very, very broad term, excuse me, and it need not actually be concrete deterministic values in it, 1 or 0s. It could actually tell you the probability of being at war. So you could have a state vector consisting of a list of probabilities for every country that tells you the probability that the country will go to war sometime next year. So instead of the state vector being 0 and 1s, it can be 0.3. And 0.3, that means, in that case, that's the chance that the country goes to war next year. And then the evolution of the state vector could tell you how the probabilities evolve over time, right? So if a country becomes increasingly likely to go to war, the probability that it might go to war might go from 0.3 to 0.35 to 0.4 and so on. So the state vector comprising probabilities of going to war would evolve over time with the probabilities increasing or decreasing. So the upshot of all this potentially very confusing stuff I'm throwing at you here is state vectors, states of a system can be very, very general, very broad, and fit your particular circumstance as much as possible to what you need it to be. And oftentimes the state itself is chosen to fit your needs. You can put more stuff into the state, take stuff away from the state, and so on. We say a state is sort of finite, countable, or it can be an infinite state, a continuous state. Typically, we're going to deal with finite countable elements in a state. When we have finite element countable elements in a state, we can call a state vector. The state vector is just a vector consisting with each element tells you a particular aspect of the state of the system at that moment. So country 1's at war, country 2's at peace, country 3's at war, 4's at war, 5's at peace, 6's at peace, 7's at peace, and so on, right? However many countries you had, that would be the length of the state vector in that case. If you had all possible dyads, the state vector might be very, very long because there are many, many, many possible dyads between, several hundred countries. So a state vector would have, 1 would mean war between country 1 and 2, 0 might be between peace between country 1 and 3, 1 war between 1 and 4, and so on, with all possible dyads being represented by an element in the state vector. Again, a state vector can be very complicated or very simple, depending on what you need it to be. Okay. Those are the states of the system, and they're represented here by state vectors S. And the sub t means at time t because we're dealing with dynamic processes here, dynamic processes in which the system evolves over time. Now, this over here is a transition. It gives you transition probabilities. It tells you the probability of transitioning between any two states. So if you have a continuous state space, and I should say state space is the space of all possible states. If the state space is continuous, then the transition probabilities might be functions where they take as input some value of the state space and spit out another value. But when you have a discrete space, a finite discrete space, countable elements in your state space, then the transition probabilities often take the forms of matrices. And now you'll see why this is coming up in this particular lecture. When you have matrices, when you have a matrix T, it tells you how to transition between one state and another state. And there are different notations for how to do that and different frameworks. Here I'm multiplying T from the right to get to S of T. You can also multiply it from the left. It depends on your point of view. Here S is a column vector. You also sometimes see this written like that, where here these are row vectors. It depends on your point of view. The idea is this. Let's say you had a two-dimensional state vector with elements 1, elements 2. And you want to see how it gets, and this is at time t. And then you want to see how it ends up going to something else at time t plus 1. Well, you need a matrix here to multiply different states. And the idea is, how do you end up getting, here's T11, T12, that's T, sorry, T21 and T22. Well, the idea is this. Matrix multiplication says that T11 S1T plus T12 S2T is going to equal S1 T plus 1. So the first element of the state at time T plus 1 is going to be this plus this. And what do those mean? The first one is if you started in state 1 in the previous period, this is the chance you stay in state 1. So T11 here is the chance you remain in state 1. Here, if you start in state 2 at time t, T12 is the chance you go from state 2 to state 1. So in this particular way of writing it with column vectors, T12 is the chance you transition from state 2 to state 1. And that's what's called a transition matrix, transition probabilities, and transition matrix, because it transitions you from time t to time t plus 1. Same thing down here. Here's the other stuff. Well, this one over here tells you the chance of, if you start at state 2 in time t, the chance of staying there is this T22. And this first one, if you start in state 1, what's the chance of moving to state 2? Well, it's T21. Tells you the chance of moving from state 1 to state 2. Because you have to end up somewhere, so if you start at state 1, you have to either go to state 1 again or go to state 2. You have to be somewhere. T11 plus T21 has to equal 1. So the columns have to add up to 1 in this formulation, right? Because S1, the first element, must go somewhere. If you started in state 1, you must end up in either state 1 or state 2 with some probability. Therefore, the sum of all the ways you could move from state 1 has to equal 1. So we know that t11 plus t21 equals 1, and similarly t12 plus t22 equals 1. So this is a way of sort of setting these things up with transition probabilities. It tells you basically what the chance is you go between states. If I had something like this, 3/4, 1/4, 1/4, 3/4, these symmetric transition probabilities. This would basically mean you got a 75% chance of staying in the state you're in. So, and then a 1/4 chance of transitioning to the other state. And that's a way of representing the evolution of a system where the rules for changing between states are probabilistic. Okay. Such transition probabilities. These can be extraordinarily general. So here we have numbers, but in general, these transitions can be anything. It need not be a matrix. It could be some complicated operator on your states. It could take into account all the history of the entire universe that went before this transition, right? It could be the case that way back in the dawn of time, a rock moved once, and that rock's movement affected the behavior of the state billions of years later. That's entirely possible. It could be, the transitions could be vary constantly over time. They could be continuously varying, right? In terms of like, they could update your states continuously, right? Just constantly changing over, with every instant in time. So in general, this can be very complicated. Now, oftentimes we simplify this stuff. The first simplification that we see is to assume stationarity. A stationary stochastic process is one in which the rules for transitioning between states don't change over time. They're stationary. So if there's a 3/4 chance of staying in the state 1 at time t, there will remain a 3/4 chance of staying in the state 1 at time t plus 1, and so on forever. In contrast, a non-stationary process could have the chances of transitioning between states varying over time. We're going to pretty much assume these things and the stuff we're talking about here, and oftentimes, for most stuff you'll see, this is going to be assumed, a stationary process. Non-stationary processes get very messy. Okay. 2, a Markov process, and the Markov assumption is an assumption of memorylessness. It's an assumption the process is memoryless. This means is the transition probabilities are not conditioned on anything that happened in previous periods. They depend only on the state you're in now and the transition probabilities themselves. So the chance of being in the new state, in each element of the new state, depends only on the state you were in previously and the state and the transition probabilities. This is often paired with stationarity too. This is often known as history independence, right? Well, I shouldn't say that. That's not true. Scratch that phrase there. What I'm trying to say is these things do not depend on past history. They don't require you to have a memory of what happened before. They depend only on where you are now. You've seen on these before. If you're playing, say, a board game like Monopoly or whatever, and you have a couple of dice, the chance that you end up at any particular point in the board depends only on where you are now and on the roll of the dice. The dice here dictate a transition probability, and the point you're at in the board now is your present state. It does not depend on anything that happened before. It doesn't matter how you got to that state. All that matters is that you're at that state now. You're at that position on the board now. Other processes are limited memory processes, which is a sort of broader term, limited memory. A limited memory process is a process in which there is memory that matters, but it's more limited. So for instance, when you play cards, you deal out cards, the deck gets drawn down. As the cards are removed from play, the chance that you could end up in different states, i.e. having different cards in your hand, changes. Right? So if you have a fresh deck, and you're playing, say, blackjack with people, and the cards are dealt out, right? The chance that you could then draw another card and get closer to 21 changes depending on all the cards that are handed out. So the probability of transitioning to different states, i.e. different values of your hand, changes based on what's been done previously in terms of cards being distributed. That said, this is still limited memory. It's not forever memory, because eventually the cards get picked all up and shuffled again, and it starts anew. So at that point, all prior memory doesn't matter anymore. You start fresh. So it's not so you don't require you to know the history of the whole world. In sort of more practical political science examples, you might think the chance of going to war depends on prior history. It certainly must depend on if you're at war now, right? But it might also depend on prior history of war, because you might have built up bad blood between two nations and so on. Then again, it might not depend on forever history of war, right? Does it matter that the people who lived in your territory 7,000 years ago, who might have been a completely different ethnic, religious, racial group than you are, went to war with some other group in some other nation who doesn't exist anymore, right? That probably doesn't matter as much anymore as more recent history of conflict between two countries. So here the memory might be not purely memory of this. It might just be limited memory. That said, it'd be wrong to believe that Markov processes are really constraining, because they're not. And the reason they're not is because the state vector can contain so much information that you can actually put a lot of summary information about the state and about prior history directly in your state vector. So, for instance, you believe that prior history of conflict should affect your chance of going to war now, and not just whether you're at war now or not. One way of doing that is to incorporate a long memory process in which you take into account all the prior states of the world in terms of conflict beforehand. But another simplified way is to add up all the previous years of conflict and use that number of years of prior conflict as part of your state vector, and just keep track of how many years of conflict there have been in the previous 50 years. That particular element of the state vector will depend only on the present state, which is how many years of conflict you had previously, and the transition to conflict or not in the next period, which would either add 1 to your count or add 0 to your count. So you could basically, by adding these summary measures into your state vector, you can actually incorporate a lot of effective dependence on prior history into your Markov process without actually requiring it to remember everything that happened beforehand. So in effect, as long as you don't require the actual fine-grained details of everything that happened beforehand, you can incorporate a lot of information as summary measures, summary metrics in your state vectors. So for instance, you could take, instead of having, war and peace for two countries, you could have number prior wars as a third element in your state vector. And you just update that in the same way you update everything else. And then your transition could depend not only on present war or peace, but also on the number of wars you've seen before. So you can actually be pretty general with Markov processes, and we're actually going to assume most of the time Markov processes and stuff we do, because it's a lot easier to deal with when you can constrain the dependence on prior events. And putting the two together, you actually get a nice simple way of representing things. The third assumption you often see is discrete time transitions, the discrete time process. The discrete time process happens in discrete time, so it's a step-by-step process, right? So at time t over here, at time t plus 1 you transition to a new state, at time t plus 2 you transition again, and so on. It's a set discrete time process. It happens in discrete intervals of time. Continuous time process happens continuously. You constantly are changing your state, with every instant in time. Typically, we're going to want to use discrete time processes because they're much easier to deal with, and also most of our data, as we talked about in the previous module, most of our data is measured discretely. We don't have truly continuous time data, so effectively we can consider most of the data are done discretely, so we can consider the transition between data at point 1 and data at point 2 as a discrete time process. So that's that. So those are the three assumptions we often see. We often will take the two things together and call them a Markov chain. Sometimes you will see it referred to as a discrete time Markov chain or continuous time Markov chain. Sometimes you will confusingly have this discrete time added to the same definition of Markov chain. That's really, it doesn't, I mean, it's used sort of indifferently most of the time. Basically, you either see a Markov chain referring to any continuous or discrete time stationary process with a Markov assumption of memorylessness, or you might see it refer to only versions that have discrete time transitions. That's the setup. In the next two modules, we'll talk about a little more details about them. But before we do, a couple words on how they're used. There's a couple really common usages you'll see. The first usage is in stats, when you deal with things called Markov chain Monte Carlo simulations. The idea is to simulate out properties of things like estimators in statistics by just running through a Markov process, a Markov chain, a stationary memoryless discrete time chain in which you build up the sort of posterior distribution of something over time using random draws. And that's really, really rough. You'll learn a lot more about this in your stats classes. But Markov chain Monte Carlo, often abbreviated as MCMC, and there are packages in your stats programs to apply this type of approach. This is all you're doing. You're using the technology of Markov chains to understand better properties of your statistical properties of various things. So that's one common use. A second common use is as part of games. There's a game theoretic equilibrium called Markov perfect equilibrium, in which you basically take a sequential game in which events happen sequentially and put in some kind of state of the system to which actors respond, and the state will update according to a Markov process. And then individuals must respond not only to the present state, but also to how the state is going to evolve over time based on their own actions. So the state only depends on where the state is now and the actions of the players, and the state transitions, and you must pay attention to that transition as well. A third way you'll see it is in models of bounded rationality, in which you have assumptions of irrationality on the part of players. A lot of models that involve bounded rationality use stochastic processes pretty heavily, in which the chance of ending up in a particular state of the system, corresponding to some set of actions maybe, will depend on where you are now and on some transition probabilities based on exogenous events and what you're doing now and so on. So you'll see these stochastic processes used in a bunch of boundedly rational models. So these come up again. This is a little more advanced topic than some of the stuff you've seen in the previous two lectures. So if you watch this module just on a lark and you think this is a little too advanced for what you want to look at now, you could just skip this and come back to it later. It's there for you. It's not going anywhere, so you can look at it later. That's because if YouTube crashes. But it's there for you. You can look at it later and learn more about this. Otherwise, we'll go on in the next two modules to talk more about Markov chains and some of the properties of stochastic processes in general. Thank you very much.